Cool. Today we will talk about the audio domain generation. But before that, quick reminder, we were doing project pitch on Wednesday, so prepare on that, and we can always figure out another time to talk about the project. This is much brighter. Um, so yeah, we've talk about the piano roll generation thing. So just quick recap. Basically, the idea is that, CNN sort of fit the idea of that reusable pattern thing. So we're thinking about, can we use some of these image generation model to do this? Because there are repetitive patterns that we can potentially reuse some of the models we know in, image generation. So first thing we talk about is this GN idea where these two components are playing this adversarial game where one tried to cheat the other tried to tell real from fake. So we can actually use these models to generate, piano roll in this case turn 90 degree, but you can see that it sort of like figured out which octave where to play that particular note, and we can extend that to multi-track scenario, multi-instrument. So in this case we are generating music in 5 tracks. Basically we just merge, grab a MIDI file, and there are multiple, potentially multiple tracks for piano, multiple tracks for guitar, but anyway, classify them, categorize them into these 5 different groups, and we will get something like this. So over the time when the model is training, you will see that the model gradually learn to allocate the note into the correct shape, like chords or without chords, or like bass, it's just monophonic. For drums, you see the patterns. So these are like called generative adversarial networks. Sort of the first thing, the first time people thought about, well, Gen AI could become a thing back in 2014, 2015-ish. Um, and we talk about diffusion models. So this is the model behind some of the most, sophisticated image generation models nowadays, even though it's somehow more computationally intensive, but people are also looking into ways to improve this. So the idea is that, on one direction, we just keep adding noise to that. On the other direction that we are learning is to see how we can remove those noise. So think about doing this for 1,000 steps. So, basically you will learn this model that go from like pure noise and remove the noise all the way until you get the real image. Sounds like magic, but there's some principle that you have to follow. It's not just about just removing noise, but the idea is that, we know these kind of denoising autoencoder that has the ability to find the patterns and remove those noise that's, just occasionally, rarely found in your image. So usually T will be larger than the 1,000, but people are also looking into ways to improve this so that you don't need to do the whole iterative process. You can jump, or you can even just do one step jump. But anyway, you can use this kind of model to generate, piano roll. So in this case, still the same idea. Go from noise, keep removing stuff, and you will see some patterns showing up. And at the end, you get the piano roll. So we look into this idea. You can extend it into, cascaded diffusion model that generates stuff, find, cores to find generation idea. And so that's diffusion and GN, but we also talk about some of the other kinds of model that's sort of like doing infilling. That's using the context to fill in some of the notes. So you can do this iteratively. So there's also this coconut model that also try to do this in that way. Um, so something like this, where you are not just generating the music directly, sequentially, I mean, but more like using the context to refine what you are generating. And we also talk about some of the control level music generation models. Cool, I will skip this. But today we are going to talk about audio domain music generation. So we will get to this, but we will start from generating music in audio domain, which basically means waveforms or spectrograms. But at the end, what you want to get is not just about the sheet music that you have to use synthesizer to synthesize it, but rather just the audio directly. Cool. Um, Cool. As we talk about, there are like four paradigms of music generation. Symbolic music generation, we've talked about, text-based, MIDI-ish, one by one, language modeling, image-based, more like image. So you can generate just as if it's like image. So it's like more parallel and you are learning some of the patterns and you're copy pasting or, think about stamping different, chords on the piano roll. But today we were going to look into audio domain music generation. So this basically can be categorized into two groups. So one is like looking at this waveform. It could be, 16 kHz, 22.1 kHz, 48 kHz. But people are looking into how can you just generate these time series. So think about time series is actually a huge field that people are very interested in machine learning because, think about, earthquake, waveform modeling, or think about stock price, high frequency trading. Or think about, medical signals. Those are a lot of them are actually time series based. So there's also a lot of like machine learning models for time series based model for signals. Image based, then spectrogram, you can see how it's just look like piano roll in some sense. So you can imagine whatever that work on piano roll, like GN diffusion models, can sort of likely work on spectrogram. And that's essentially the case. And on Wednesday, we will proceed and talk about this very confusion latent space based systems where basically you are merging some of these together and you are generating something sort of like generating MP3 byte rather than generating the audio directly. We will see it on Wednesday. Cool. So generating waveforms using a neural network, it sounds like a crazy idea, but actually back in 2016, people already trying to do this and it somehow it works. So, as we talk about waveform, it's just like, a bunch of points that, you know, between 0 to 1 or minus 1 to 1, whatever that range is. But it's basically measuring the pressure of, the sound, the air, basically. So the idea is that can we use some kind of language models to do this auto-regressively, given the immediately previous air pressure point? Can you predict what the next one is? And that happens in 16 kHz or 48 kHz. And somehow it turns out that it is possible, even though think about it, how crazy that idea it is. But basically, following the same idea of all these language modeling, what we are trying to do, what would be the next word to be? But think about now, we are turning it into another way. So language model is like, even though the previous word, what's the most likely next word? Now, what if we think about numbers? So we have a bunch of numbers. Those are, the air pressures, like waveform, 0.9, 0.8, 0.7. What would be the next one? So that's essentially what they are trying to do here to do waveform modeling directly using autoregressive models. So think about 0.5, 0.4, 0.3, 0.2. What would be the next numbers could be? So in this case, if that's some patterns there, 0.1, 0.09, 0.11 sounds likely. But on the other hand, jump to 99 minus 1 could be less probable. So, this idea of autoregressive actually can be extended to waveform, even though it sounds crazy. But, deep learning models are crazily powerful. And so people just try it and somehow it works. So that's the idea. So, the under level, the fundamental idea is the same, that we are just trying to given a bunch of previous numbers, what would be the next immediate numbers would be. But there's a tons of, training challenges and also modeling challenges so that you can grab enough context that we will see later. One thing that's a little bit confusing is that this term autoregressive has different meanings in machine learning and signal processing. So this is sometimes when we were talking about, autoregressive waveform modeling, because waveform modeling is traditionally a signal processing thing. But in signal processing, an autoregressive model needs to be a linear model, which is not the case in machine learning. All the machine learning model is sort of built to be modeling nonlinear model. That's why we are using deep learning. We have all these, activation. We have all these layer by layer so that we can model nonlinear model. Linear model, it's not mostly the case, not what we are interested in deep learning. So this is one of the things that sometimes confuse a bit when you are reading literature in different fields. When you're reading like machine learning papers, they will be autoregressive in one definition, but in signal processing, that's another definition. Cool. But anyway, that's the idea. Grab a bunch of past information, aggregate them to try to predict the next one. So this is a nice, animation of that very iconic model called WaveNet, where we basically just trying to grab all the previous inputs and try to guess what the next output will be. So you can see in this case, it's actually trying to aggregate a lot of information in the past that you are basically grabbing 2 by 2, grouping them. And then, so the way you look at how much context you are doing, so all the way from this to this, just going over 4 layers. So it sort of like grow exponentially. So compare this to a traditional neural network, convolutional neural network. Where's my okay. So compared to a traditional convolutional neural network, which usually look like this, there's some overlap, and you sort of try to aggregate them together. So if you look at this, it grows sort of like linearly. After 4 layers, you get 5 of those. But in this case, this is what we call dilated convolutional neural network, where basically all of these the context, or what we call the receptive field. Here, the receptive field grows exponentially over the layers. So this is the difference between WaveNet. So because in WaveNet, think about we are trying to do waveform, and we talk about that the Nyquist, also the Nyquist rate and the sampling theorem. So you sort of know that you need enough number of samples so that you can grab that frequency. So think about what you need when you are predicting the next note, next sample. If you are doing something at the left-hand side, you only get 5 of that immediate samples. How can you guess what the next one would be? Because there's no way you can sort of like do some FFT to understand what would be the frequency. Then how do you know what that immediate next output will be? But in the dilated convolutional case, where your receptive field is huge, so there's some way you can actually analyze some of the frequency component hidden in this large context that's provided to the model. But basically, the idea is just a traditional convolutional neural network, just that the way how you do the stride, like how you jump and how you design the filter size and how you divide the pattern. So basically those, parameters in convolutional neural network, you have to design it so that it just like the receptive field will grow exponentially over the layers. So imagine that you are doing 44.1 kilohertz waveform modeling, then, just 5 samples here will be, I don't know, maybe just 1 millisecond-ish for, 44.1 kilohertz. So, 5 divided by 44,100, that would be pretty small, right? That would be less than a millisecond. But in this case, if you have more layers, you can imagine that it becomes something like 10 millisecond, 20 millisecond, 50, even 100 millisecond. Then it's meaningful amount of information that you need to predict the next sample. We can listen to some of these models. So this is actually using the same data sets that we talk about in performance RNN and music transformer, that piano competition um, data set where they use this kind of like player piano to record um, the performance. But now we are using row waveform as the training target. Okay, let's see if I have the right. Cool. So what you're hearing is actually just just a convolutional neural network. You're given as some sort of like pre-melody and let it generate one sample by one sample over the time. Cool. Another example. So you sort of get the idea of WaveNet, where it's like an autoregressive model. So oftentimes when you listen to example generated by autoregressive model, it will sort of like explode later in the stage. The reason is that, it makes mistakes, right? Every kind of predictive models will make some mistakes, but later in the time, because it depends on the previous generated outputs. So it depends on some of the mistakes it has already generated. So that mistakes will just sort of like, escalate and, amplify over the time. And at the end, it's sort of like based on all the wrong, incorrect or doesn't make much sense output, and it will keep just sort of like explode and this won't get anymore. But this is, the first time people are trying to generate something just using convolutional network directly on waveform, and somehow it works to some extent. Um, Questions, or we can look into this very cool effect that, this is just to sort of give you a hint why WaveNet can be done. Because, think about this way as like, well, let the human look at these waveform, look at the numbers, and you are imagine that given 1,000 points and you want to guess what the next, air pressure would be, that sounds impossible. But turns out, if you look into some of these 1D convolution neural network, what we are using here, even though this is doing autoregressive modeling, and in this case, they are not doing just purely autoregressive modeling, but basically they found out that 1D CNN are kind of doing some kind of Fourier transform. So this paper, they are doing acoustic modeling for roll type signals in LVCSR. It's like a speech recognition task. But anyway, they figured out that, these are some of the 1D CNN filters that learn by these convolutional neural network. So, this is one of that, this is another one of that, and this is another one of that. And so if you remember the STFT thing, this is basically a sine wave with the window applied, right? You have the hanging window here, and you have the hanging window there. So you will have that Mexican hat shape thing, or think about wavelet analysis. And D3 has sort of like different frequency that it's detecting with this. Where's my cursor? Yeah, this one has a higher frequency. This one, has lower frequency. This one have even lower frequency. So it's very interesting to see that, these convolutional kernel, 1D convolutional kernel, are actually learning these different frequency. And you can sort of imagine that these models what happened with these model is like grabbing these filters and imagine this is your examples and use this to slide around to see whether you detect that frequency. And that's essentially, before when we talk about spectral analysis, when we are doing Fourier transform, that's essentially what Fourier transform is doing. So at the right, they can you can actually do Fourier transform on this kernel and that kernel and that kernel, and you sort of can grab what the frequency that these kernels are detecting. And this is the graph. This is a plot where you show all these hidden kernels and you arrange them with the frequency. So for um, so basically, you have a bunch of these kernels and you just plot where they are. This is the first one. It detects this frequency. The second one detects this frequency all the way until it reaches somewhere here, where you basically have 8K is the maximum because you are doing 16K hertz modeling here. But you can see that this is essentially Fourier transform. You have different kinds of convolutional kernels where each of them are handling different frequency. So I guess that's essentially what I want to talk about in this wavenet thing is like, to be honest, we don't really know what's going on within these models. It just sounds crazy for us to think about, just for human, like how do you even guess what the next air pressure would be given just a thousand previous pressure measurement. But this could give you some hint that it potentially could be doing, given the previous 1,000 points, do some Fourier transform, then you sort of know there's some frequency going on. Then you can combine all those frequency, add them together to sort of guess what the immediate next point would be, because you know how those frequency move over time, right? So again, we are still not quite sure. These is very powerful models that somehow just learn to do this. And this is the first time that we can sort of use just a very powerful machine learning model without a lot of prior knowledge, just to let it train autoregressively. And somehow we show that it does generate waveform in an autoregressive way. And nowadays, these are applied in a lot of like different modeling. So think about, I guess finance is the biggest thing where people are thinking about stock price prediction, but also high frequency trading. So a lot of these are time series forecasting, or weather, temperature prediction, humidity prediction, or medical signal forecasting to see whether these medical signals or doing denoising. A lot of the ideas come from those time series phase signal modeling. Questions? That would be the only one we will talk about time frequency, time domain audio synthesis, because pretty much there are few ways we can do time frequency, time domain audio synthesis. Oh, good. Cool. Then, we also have frequency domain audio synthesis. Then it's not that fun either way. So think about, whatever you can do on piano roll, somehow you can do on frequency domain, because it's the same idea. But one thing it's a little bit different in this case is that, we have to turn that spectrogram back to waveform. So usually these kind of frequency domain audio synthesis, we have to think about it as two different models. The first one, there's no actually a name for this. But anyway, the synthesis model that we typically refer to is the one that generates spectrogram. So you can imagine like generating a spectrogram, you are sort of like 80, 90% done. Because as we talk about, spectrogram is only the magnitude. It doesn't have the phase information. And usually the phase information is not too tricky to get, even though we will see later, it's also not trivial to get the phase information, but I would say spectrogram already contain 80 to 90% of information. But the last step, nowadays we have a sort of different models that can do the last step from spectrogram back to waveform directly. So the importance of phase information, even though, as I said, face is not that tricky to reconstruct, but if you're using random face, it still sounds weird. This is the real audio. So this is the one that you have a waveform. You turn it into spectrogram with magnitude and the phase, and you want to reconstruct it. That's what you get. But now, looking at the face, this is the real face information. And you might look at it and think, this is just pure random noise. What if I replace that with a random face? This is what it sounds like. So it's weird, but it does have those frequency. It's just that, all these notes are just like playing on a very sort of bad piano kind of. So that's, sort of like importance of the face information, but also that, you do require that 10% amount of details so that it sounds real. But still, lots of information is already contained in the magnitude of that spectrograms. So the idea here is just that, well, can we reconstruct that face information? So, this is one thing you can do in the Rosa directly. So inverse STFD without face information. So what you can do is that you can actually just grab a Fourier and audio, and you can actually try to find the signal Y that minimize the MSE between the inputs and SDFDY. So the idea here is that this is doing inverse short-time Fourier transform. So whenever you want to do inverse short-time Fourier transform without the phase information, what you would do is that you grab that so what you will have is only the magnitude of your SDFD, and you don't know the phase information. And what you want to do is try to find that audio that has the closest magnitude of SDFD to your given magnitude spectrogram. So what you can do here is imagine that is our input signal. What you are doing here, what you will get is something like this. So it doesn't really work. This idea is that, well, hopefully, in the ideal case that you might imagine that given the magnitude only thing, you could imagine that you can find an audio signal that perfectly reconstruct your magnitude only spectrogram. And this is essentially what this optimization thing is doing, because you are trying to find that audio that has the SDFD the closest to what you give it as the input. But turns out this is what you get. If you just use this as grab this, get the magnitude, and try to find that audio signal that has the closest magnitude only spectrogram to that, this is what you get. So it doesn't make much sense, right? It does have those frequency, but it just, just looking at those, it doesn't look alike. So this doesn't work. So one thing that people have been using in the past before deep learning is something called Griffin-Lim. So the next few slides, I will introduce what this is. This is a very important algorithm that people have been using to reconstruct spectrogram back to waveform. But nowadays, we actually have a lot of deep learning models. But this could sort of give you the sense why this is doable, that phase can be sort of reconstruct from the magnitude to some extent. Not perfectly, to some extent. There's a lot of prior knowledge that we can use. Cool. So the same signal that we have, so this Griffin-Ling algorithm works like this. So given a magnitude only SDFE matrix, so imagine that you have this signal, but you don't have the phase information. You only have the magnitude only SDF matrix. You just randomly initialize the phase. And then you do this. So the same idea previously, you have the randomized phase, and now you want to find the signal that minimize the MSE between the input and STFDY. So what you are doing is that you have the signal, you have the magnitude, and you want to find that particular audio signal that has the closest, um, the closest magnitude only spectrogram to your input spectrogram. And then you'd find the SFT of the signal Y, assuming you have the initial phase of that. I don't think this is actually needed. And the idea is that you just keep doing this again and again. So the second time, once you have this Y, you just do the SFT again on that. Well, I should explain it a little better. So the idea is that you're given a spectrogram, you try to find that audio that closest to that spectrogram. And once you figured out that Y prime, that's a better estimation of what you have for now, then you do this and you find that magnitude of that. And then you do this again and again. So this is sort of like try to predict the audio given the magnitude, then try to predict the magnitude given the audio, and you do this again and again. So it's a little bit similar to, oftentimes I think it's sort of similar to that, pseudo Gibbs sampling thing, where, initially everything is randomized and you don't know exactly what it is, but you just do it again, do it once, and then you fix something. And then you do it again and again, again and again until it's sort of like figured out, sorted out all the context information. But anyway, this is Griffin-Lim algorithm where the idea is just that, well, let's just keep doing these things again and again so that over the time, it will figure out how to remove all those artifacts that doesn't make much sense. This is sort of when you do 32 iteration of Griffin-Lim reconstruction, what do you do? This is the original one. So anyway, you can still see that they are sort of different in the, maximum, the range. But at least the shape is not too bad. So this is like before deep learning era that people have been using this. And if you look at the year, it's 1984. So pretty much for 3 decades before 2014, people are using Griffin-Lim to reconstruct the actual waveform from the spectrogram. Anyway, the next few slides, we will see the deep learning equivalent to that. And it's kind of boring because, deep learning model is always, well, you design this model, that's cool. You have to spend a lot of time designing these models. But to be honest, these models are just being trained to do that. And somehow it nails it. But these are some of the models that we've seen actually. So the first one is mel GAN. So you see GAN, so generated adversarial networks, but in a slightly different format. But the idea is that what we want to do is that, well, we have this spectrogram. Can we get the waveform out that is essentially what we want, right? We have the mel spectrogram and we want to get the waveform. In this case, we are sort of like thinking about, can we reconstruct the phase? But, essentially what we are interested in just that, well, we don't necessarily need to care about the phase. We just want the final audio. You can reconstruct the phase in the middle of your processing. But basically, this is the idea. So there's a GN. So what's going on here is that think about the resolution between these two things. At the top, it's like SDFD. And we talk about SDFD, we will do a lot of like windowing, we would do a hop size, we would do filter size. So it's sort of like aggregating information over time. So the temporal resolution is much smaller than this raw waveform. This one could be, 16K hertz, 44.1K hertz, but this one is usually, for every, 10 millisecond, 30 millisecond, you only get one slice of F50. So their temporal resolution there's a huge difference. And that's essentially why you want to do a bunch of upsampling layer here. You see that this is like 8 times upsampling layer and two of these upsampling layers, and you will have 2 times upsampling layers here 2 times. So you will see a lot of upsampling going on. So that's essentially what this deep convolutional GNN is doing, where input is something very low resolution, only 100. But at the end, what you want to grow into is potentially could be 1024 or something even bigger. So growing resolution using convolutional network. So that's essentially what these male GANs or all these vocoders are doing. So imagine in RPA, this essentially you might be familiar with. So what we have in this case, a 64 by 64, right? We've seen that you can actually do instrument classification to some extent. Not too bad. Not perfect, but it's not too bad. So you grab one of these slices, and what you want to do with these vocoder is that, can you do something like this? This animation doesn't look right. But anyway, you will grab it and then you extend the temporal resolution over time. So you see that the temporal resolution become bigger and bigger and bigger. So in this case, this very tiny slice is like 10 millisecond, but think about 44.1 kilohertz or 16 kilohertz waveform. That would be a ton, at least 1600 of samples. So you need a much, much larger resolution, much, much larger resolution for that, many points to generate. So you want to grow the resolution, but at the same time, you want to shrink the channels. So you can imagine what's going on with these vocoders. I'm sort of like simplifying things a lot, but you can imagine this is the channels that you have, but the channel just keeps shrinking over time. But your resolution grow at the same time. So if you think about that way, then you sort of understand, this convolutional neural network, how it play with this resolution, sort of like stretching and compressing idea. So that's essentially what this male GAN is doing in all these internal upsampling layer. So, it's basically just growing the resolution, but shrinking that channels that you want to keep the additional information on those. Cool. Um, so that's essentially what's going on. You grab a slice and you try to expand, expand, expand on all the way until you get the exact, waveform that you have. And for all the slides, then you do that convolutional neural network, then the output would just be a bunch of numbers. That's just 1D output. Question on this? Sound like magic? Well, the model is doing the magic, not us. But this is essentially what's going on under the hood for these vocoders. So vocoders we are talking about for music, but vocoders is actually much more. It is called vocoder because it's actually used in speech processing early day. So landline. So if you're calling someone with a landline, it actually traditionally it would encode your voice into a very compressed digital format. We talked about previously that telephone is encoded only using 8K hertz, right? But it's much more than that. Actually, your telephone in the early days, not the mobile phone, the landline is actually resynthesizing your voice. And that's essentially why sometimes someone call you in the past and you couldn't recognize at all who that is. Because it's actually resynthesized that sounds at the moment at the receiver side when you are picking up the phone. And that's why this term is called vocoder, because you have some information and you try to reconstruct that vocal. So in this case, you have some information of what the pitch would be, some tiny bit of information, and you want to reconstruct the original waveform. And that's essentially why these things are generally referred to vocoder. Cool. There's some additional details here where, this thing is called a GN. So there's something going on, right? It shouldn't be called GN if it's just, a convolutional neural network. This is just a generator. So this discriminator, there's a bunch of stuff going on, but I would just tell you a little bit about what's the high level idea. But the idea is that there is some multi-scale discriminator going on. So think about the output. It will be 44.1 kilohertz. Of course, that's what we are aiming for, but it could be 16K hertz. But this multi-scale discriminator is just trying to see, can we downsample the output waveform, but still try to do discriminator on different scale. Sometimes we work on a very fine grain sampling rate. Sometimes we work on a lower frequency sampling rate. There is also multi-period discriminator. This is designed to actually be just reshape that things into this. So you can apply 2D convolutional layer on top of that. So this is sort of like doing Fourier transform internally. But basically, BellGN is just like thinking about what are some of the different way to design these discriminator so that it can handle this kind of very high sampling rate stuff, where 44.1 kilohertz, meaning that you need 44.1 thousand samples to represent just only 1 second. So it's a vast amount of information. So in this case, they're just thinking about how we can design this discriminator so that it works much more efficient. Anyway, there's actually another example of that, just a much better model based on the same idea. It's called Hi-Fi GAN. But if you look at these kind of model architecture, they're essentially doing the same thing. It's just in a different shape. Male spectrogram going through a bunch of convolutional transpose, basically transpose convolutional neural network. And inside it is a bunch of residual block. But anyway, what it's essentially doing is just the same idea. Grab a slice of spectrogram, and then you grow this resolution while shrinking the channels to get your outputs. We can look into some of those examples. But nowadays, actually, I would say this is almost 90% solved, kind of. I think these are usually speech.
This commission
This is the ground truth.
can
That's not what it should be.
this commission
Wait a second.
This commission can recommend no procedures for the future protection of our presidents, which will guarantee security.
So the one that we talked previously, Mel G WaveNet, we also talk about this, right?
This commission can recommend no procedures for the future protection of our presidents, which will guarantee security.
You actually sound quite good already.
This commission can recommend no procedures for the future protection of our presidents, which will guarantee security.
This is the best model, Hi-Fi GAN V2.
This commission can recommend no procedures for the future protection of our presidents, which will guarantee security.
Anyway, you can see the tiny nuance in the vocal, especially the higher frequency part that most of these vocoders are struggling with. Anyway, this is like how you can do this, vocoder thing where you can generate the spectrogram. If you can do the spectrogram generation, then you can generate the waveform. So once again, here we haven't think about, how you can generate these spectrograms, but anyway, you need to think about how you can go from spectrogram back to waveform. And here I'm just trying to persuade you that this is almost solved to some extent. Most of the hardest part will be how you get the spectrogram rather than how you get the waveform back to from the how you get the waveform from the spectrogram. Cool. So the next few slides, I would talk about this differentiable digital signal processing thing, which is very cool. So the idea, we sort of hinted about it last week when we the last slide. But basically, the idea is that can we sort of like break down the DSP thing into something differentiable so that we can train a model to do this breakdown thing. So the idea is that we have some audio where we have, I still don't have that. I can play it for you here. So we have, say, audio. So this only works for monophonic. There's some extension to make it work on polyphonic. But basically what you do is that, well, grab that audio you just listened to. And first thing, this encoder is actually a pre-trained F0 estimator. We talk about, pitch recognition, fundamental frequency extraction. That's essentially what we see in Auto-Tune and Melodyne. But it's not a very tricky job to extract that F0. And to get the loudness curve is also not too tricky. Basically, you just grab it and just compute the energy, and you can pretty much get a loudness curve. It's just, even looking at the the waveform, you see that envelope. That's the loudness curve that we are talking about. So the idea is that, well, now we have the F0. Can we sort of use these F0, the harmonics, and you sort of know what that timbre is like when you are doing this encoder. That's essentially where you have the Z will track how much, what would be the percentage between those different harmonics. That's essentially determine the timbre, right? So that's the idea. So you will have harmonic audio. So this harmonic audio is that, think about F0, 2 F0, 3 F0, 4 F0. What would be their ratios? How long will they, sustain? But that would be the harmonic part. And the filter noise part is about subtractive synthesis, where you grab a pure noise and now you want to, remove part of that to grab some of, think about you for violin, you will have those bowing noise, but when you are playing guitar, you will have those fret noise. And once you add them together, you get reverb, then you get the synthesized output. Anyway, we can look at this. And it's trained with this multi-scale spectrogram loss, which is similar to the previous one that we are thinking about in male GM, where you just do different scale and you actually compute the spectrogram to optimize the things. But anyway, this is a breakdown. So you have the original audio. You will have this encoder and you get the fundamental frequency. Something look like this. So let me play it again. So you see that's the frequency, fundamental frequency. And you can actually also do the loudness curve. So you see some of the P's that will align with where you have the onset. Usually you will have the maximum energy. Anyway, together, these two things, you can already do a lot of things. So you can sort of like get the essential amplitude. This amplitude thing will be sort of similar to your loudness curve, right? Harmonic distribution, this is doing the things is actually doing something like this, but turn it into something like spectrogram. So it's thinking about how these F0, 2 F0, 3 F0 are distributed in your harmonics. But anyway, these two things, then you can together combine them into something like this. So this is the So you can imagine what's going on here is that you only have the fundamental frequency information and you know how loud it is at each particular point, and you sort of know how that timbre is like. And you try to replicate that with the perfect, additive things. And additive things, now you listen to it, you will realize that it doesn't sound real. It sounds too perfect. It sounds like a lab reproduction of the sounds. And that's essentially what additive synthesis is doing, because it only has the perfect harmonics of your fundamental frequency. but that's not too bad, right? So the other parts, those noise, those artifacts that make it sound real, is going from the things. So this is the noise magnitudes. So think about you have pure noise, and then you just filter it based on this spectrogram. So this is like a spectrogram mask. So you will have the pure noise is that spectrogram is like one constantly over the whole thing. But now you grab a pink noise, you grab a white noise, but apply this noise um, filter. So this is the filter noise output. So this is basically the noise magnitude. And once you have a noise, apply this magnitude mask. This is what you get. So pretty much it's always looking at those onsets whenever you have the violin, usually at the onset time. When you have the note, you will have this kind of like bowing artifact. And so actually this DDSP is just interesting because you sort of like decompose your inputs into things that's not harmonic. That's the same like idea of like HPSS, right? The harmonic percussive things, decomposition. But this is sort of like a deep blending version of that, where at the top you see that perfect harmonic thing where you have F0 and you have like 2F0, 3F0, and you see how their relative amplitudes will be. But at the same time, you have this like percussive edge that doesn't have a lot of structure inside it. It's mostly noise, but it doesn't happen all the time. So you want to model that by grabbing the noise and try to predict the amplitude or the mask on top of it to generate that. But now when you combine them, then you get something better than just the pure perfect harmonic components. So compare with the clean one. So this doesn't really sounds like violin, but once you add in these things, somehow it just becomes more like violin. Uh, the last step is doing reverb. So this reverb step is not actually part of the model. This reverb is actually they use a specific reverb estimation model to, because the whole data set is using the same, is recorded in the same concert hall or studio with some reverb. So this reverb is the same. So so the reverb is not part of the prediction for the deep learning model. And this is the input. It's not perfect, but you can sort of think why this is interesting because you are decomposing this audio into a lot of things that you can actually play with. So again, this is trained by deep learning end to end actually. So if you look at this and think about all the things in between as a deep learning model, then this is actually just autoencoder, right? Because your input and output is the same, and there's a lot of thing going on, but who cares? It's just some model, right? So this is actually autoencoder. So your goal is just to make this as close to this as possible, and you are also using some spectrogram loss here. Basically, you grab these two, you compute their SDFD, and then you just compute the IMAPs between them. That's essentially what this multi-scale spectrogram loss is doing. And again, SDFD is something that you can actually optimize over. You can compute the gradient descent, compute the gradient over SDFD. So you can actually use that loss function to train this autoencoder. That's essentially what's going on. Well, it's cool to decompose, but what for? So actually, this very cool music by Hanoi is actually using that idea of DDSP. So
Hey, it's your boy Hanoi, and this is how to make AI-based music from Thailand.
So that that riff or that motif is actually performed on I believe it's saxophone or something. But you can sort of like do this tone transfer thing. So once you have F0, so if you look at DDSP, where's that? So if you look at the DDSP, now you can decompose your inputs into, F0 loudness, but at the same time here, you have this Z. Basically, you're decomposing your audio into F0, Z, and loudness. So in this case, well, you use trumpet, but you want to make it sound like the traditional Thai instrument, then what you can do is that, well, you use your you record something on saxophone, and you extract F0 and extract Z, extract loudness. But now you can actually grab the time instrument and do the same thing, just play something, but you grab the Z and replace it to the saxophone sounds. So now you can actually, once you decompose them, then you can remix them with different combination. And that's essentially why DDSP has been very impactful in music creation, because that allows you to do a lot of very interesting, tone transfer. That's what they call. You can grab one of the instrument, the timbre and the tone of that instrument, and apply it to another instrument that you know how to play. So that actually create very interesting ways to use these kind of model. And Hato is very passionate about this because he's an advocate on this transcultural or against monocultural idea of music, because as he explained, P9, this the Thai instrument is actually in a different musical notation system. It's not Western notation. And also think about a lot of traditional instrument, it doesn't have that. And also think about gamelan in Indonesia, or the Southeast Asia region, but also lots of traditional music. They are not in the Western musical notation. So, in the past 2 weeks, we think about, these kind of symbolic music notation, but hiddenly, implicitly, we are actually enforcing that idea that, well, if you are not transcribed above into Western music notation, then these music are sort of gone in some sense. But thinking about this audio domain music model or audio model, then there's a way that we can actually look into these model and enable some interesting generation capability on these models. Cool. That's what I want to cover on waveform, audio domain generation. We don't really talk about how we can generate the audio because we only, how we actually generate the frequency, the spectrogram, right? But we will look into some more about that on Wednesday when we talk about the latent bass music generation part. And at the time, you'll realize that's essentially what we are using nowadays. And it's very complex. It's sort of a mix of everything we talk about. But if you do want to learn more about this waveform things, you can check out this very nice blog. So Sander is the person who's been working a lot on audio generation, and he wrote a lot of very nice blogs on some of these machine learning models. Cool. 3 minutes left. But we talk about the idea of generating waveforms using a neural network. It sounds crazy, but somehow it works to some extent. That the idea is basically, well, all the previous numbers, guess what the next number would be. Deep learning are powerful, so it can actually do that. But the caveat here is that you have to provide enough context, because in this case, you have super, super long context that you need, because 44.1 kilohertz, just even you want only 100 millisecond as your context, that means you want 4,000 samples. Traditional convolutional network, it doesn't have this large receptive field. So we need to use this kind of dilated convolutional neural network. Basically is that you just jump very aggressively over the temporal resolution, temporal axis, basically. So your receptive field will grow exponentially as you dive deeper into the layers. Yeah, this is a much better view. Standard convolutional neural network, dilated convolutional neural network, you can see how fast this dilated convolutional neural grow its receptive field when it goes deeper into the layers. And somebody works, you can do this autoregressive modeling on waveform. Some of the hints or insights into these kind of model, one thing it could be doing is this 1D CNNs thing. And these are the kernels that it learns. And this just remind us as the a ending window shape, like this is what we call wavelet, basically. But it's sort of like doing this Fourier transform internally. That's what you can imagine what's going on with these kind of model. But we also talk about frequency domain audio synthesis, where the first part is the synthesis model that we didn't talk a lot about, but I just want to show you that the second part is also important, especially when you think about frequency domain audio synthesis, because the first part, you can pretty much just grab whatever image model that everything work for piano roll somehow always work with spectrogram, just that you have to do some more, normalization and reshaping. But the second part is what's interesting with these kind of frequency domain audio synthesis. We talk about the good old Griffin-Lim algorithm. It's just a very cool iterative algorithm that just do it again and again, but somehow you can do to some extent. But nowadays, people are doing deep learning to do it. And the idea is that you just grab a slice of your spectrogram and you keep growing the temporal resolution while reducing the channels. But the idea is that for each slice of this, it could be 100 millisecond. So that corresponds to, 1,000 or 4,000 samples. So you have to grow it aggressively on the temporal resolution. Cool. And the last thing we talk about is this DDSP, which is pretty cool because you can decompose audio into meaningful meaningful explicit features along with a hidden latent feature. This Z is the latent thing, but it can enable you to do this kind of tone transfer where, Hanoi shows in this, award-winning composition. Cool. We're getting close to, what people are expecting about, Suno, Udio. Recently, there's a news about Udio. So Udio is the two big AI music companies that got sued by UMG, which is not a good thing. But anyway, UMG recently reached a agreement with Udio. So now Udio can still do AI music generation, but it will be sort of like walled, where they can only share on their platform. The user can no longer download the songs generated on these platforms. Yeah. But anyway, we will talk about this latent-based music generation system on Wednesday.